Oh. Okay, we'll talk about modulation and demodulation. No. We'll talk about reactance phase and balanced modulators. I might even mention a double balanced modulator. Detectors and mixers. So modulation is just the process of adding information to some sort of carrier signal, whether it was light or radio wave, even sound. Typically, we have frequency modulation where we vary the frequency of the carrier signal proportional to the modulating signal, which a lot of times we call baseband. It's usually voice. We have amplitude modulation where we vary the amplitude and we keep the frequency constant. In FM modulation, we try to keep the amplitude constant and vary the frequency. FM receivers don't like varying amplitude. Well, that's why they have a thing called a limiter circuit to try to make it a constant amplitude. Well, then the discriminator circuit doesn't work right. So you have a limiter before the discriminator.
Stored or drop out or what?
I don't know. It doesn't work right. I never had one without that, so I don't know, but that's what it says in the book. So it must be right. And it says on the internet, so it's got to be right.
Oh.
We have single sideband, which is really a special case of amplitude modulation, where we're only going to transmit one sideband of the signal and no carrier, or we suppress the carrier. There's also phase modulation, which is almost the same thing as frequency modulation. And from my understanding, the human ear can't tell the difference. And you do it with a reactance modulator. So your modulating signal varies the reactance of a device like a varactor. Okay, and in that reactance or varactor is part of your frequency circuit. So you're varying the frequency or the phase of the signal proportional to that modulating signal. If you want to do the math, I'm sure Ed does. There's the formulas for it. It turns out that phase modulation is a simpler formula than frequency modulation. And the key to solving those is this, the integral of sine x is equal to minus cosine x. I'm sure you remember that. When we have FM or PM modulation, you see in the graph here, it's showing the frequency varying with that modulating waveform. The higher, in this case, the higher the modulating voltage, the higher the frequency, and the lower frequency when it gets down into the negative range. If you look at a spectrum analyzer, you're going to see this kind of a frequency spectrum, and you're going to see these harmonics of the baseband out here on either side of that fundamental. Similar to what you would see if you look at a AM, where you see the sidebands. In FM, you see multiple. Typical circuit where you're using the varactor diode to do the modulation. And that's, if you notice that varactor is really in series with the capacitor in your tune circuit. So that's how you're varying the frequency by changing that capacitor. And the reason is that this when blocking capacitors here, because you have to put a bias voltage on the varactor to change its capacitance value. So you have to keep that DC bias away from the tank circuit. So which of the following can be used to generate FM phone signals? Well, you have to pick one.
Baker.
Bravo. You got to modify the oscillator. What is the function of a reactance modulator?
Delta. Drain the capacitance.
You're kind of limited. As far as I know, there's no voltage variable inductor.
No.
So you're kind of limited to a voltage variable capacitor called a varactor.
Might be able to do it with a gyrator.
A what?
A gyrator circuit.
Oh, yeah. An active one?
Yeah. Oh, yeah.
Yeah.
I know the term, but I can't remember anything more about them.
Yeah. I remember it too, but I couldn't draw it right now. For FM modulation, a lot of times they'll add what's called a pre-emphasis network. So they can boost the higher frequencies, similar to what you see in a amateur radio compression, where you're essentially shifting the audio frequencies towards the high end. They do that with the pre-emphasis circuit in FM transmission, and you'll have a de-emphasis circuit in the receiver. No, not Dolby. And part of the reason they do that is so it's compatible with phase modulation. Because sometimes, like if you saw the formula, it's easier to generate a phase modulation than it is a frequency modulation. The end result is pretty much the same. This is a typical pre-emphasis and de-emphasis circuit. They're fairly simple. They're just doing a little frequency. So what is added to an FM speech channel to boost the higher audio frequencies?
David.
Delta.
Why is de-emphasis commonly used in FM communication receivers?
Alpha.
Yep.
Alpha. Let's see, what is this? Oh, amplitude modulation. Typically, we generate AM signals with just a mixer circuit where we actually multiply the baseband signal or modulating signal with what we call local oscillator or your VFO. And if it's a simple mixer, you're going to get out the fundamental frequency or the carrier frequency, and you're going to get the baseband sidebands on either side of it. So you'll get one of the products would be the products are the sum and the difference of the two frequencies. So that's why you see them as sidebands. You get the carrier plus the baseband and the carrier minus the sideband, the baseband. So that's the two sidebands. The lower sideband is inverted frequency-wise. So higher frequencies on the lower sideband are actually lower frequencies in the spectrum. That's why if you try to listen to lower sideband on up and you're set for upper sideband, it sounds kind of funky. It's inverted.
Or you don't hardly hear anything at all.
Well, it depends on your radio and what you can do.
Well, that's my experience.
But you'd have to change the tuning. I mean,
Well, from all. So
if you go down,
listening-
if you're looking at upper sideband, if you shift down to where the lower sideband is in your upper sideband passband, and now you've got the signal, but it's inverted frequency wise. Otherwise, all you'd have to do is move up and down and pick either one. But it doesn't work unless you filter one out and flip it to the right one. We'll talk about that a little bit more and confuse you even more. But essentially, remember that you get the sum and difference of the two frequencies. That's a simple explanation. Turns out you actually get the sum and difference of the fundamental and the modulation, and then the sum and difference of the harmonics and the modulation. Remember, we showed that intermodulation chart with all the frequencies and F2 minus F2, F2 minus F1 and all that stuff. You actually get all of those things. Usually they're far enough out and you filtered it, you don't care. If you overdrive a typical mixer circuit, you're going to get clipping, so you'll get probably third order, fifth order harmonics. Call them spurs because they're little frequency things in the place that you don't want. Whoops. When we amplitude modulate, the picture down here just shows you're varying the amplitude of that carrier wave anywhere from 0 up to its maximum. If you look at that on the spectrum, you're just going to see the carrier and the two sidebands. I'm not sure why in this case they're different amplitude.
Shouldn't be.
It could just be the point in time at which that snapshot was taken. If it was really, I don't know.
Transition.
But as the modulation changes, you will see those things move and go up and down.
Carrier frequency here is.
Okay.
So
Omega
what's
C.
the Baseband, is that the modulated signal?
Mm-hmm.
Okay. But that keeps varying, right?
Yeah. Yeah, it won't be static like in this thing. Those sidebands are going to be moving around and up and down. And much more predictable if it's a regular AM broadcast. I mean, and it's not this little, that you'd get little peaks like that if it was just a single tone, like a 1 kilohertz. Yeah. If it was voice, you get a, yeah.
And I see that on up 7300.
Yeah. Yeah. Well, you'd see this if you had a signal that just had a, you know,
Single tone.
Yeah, like somebody just keyed their, and you were slightly off on CW, just hear you the site, well, it wouldn't show up on the spectrum display. Because you're only getting the carrier.
They played a French horn or something.
Yeah,
Okay.
yeah,
You would see the carrier and then the two sides.
right. Of course, the French horn is not going to be a pure sine frequency, so you're still going to get.
To a sine wave.
Really? I didn't know that. Okay. So in amplitude modulation, we
Excuse
talked
me,
about
excuse
the
me, what,
sideband.
pardon me, Bob,
Yeah.
what was that clarification about the French horn?
He said it's the closest to generating a sine wave of any musical instrument.
Oh, okay, appreciate the clarification.
Um, let's see. Oh, okay. And we have a carrier, which we refer to as omega C. Remember, omega is just a shorthand for 2 pi f. It's easier to write. You also have a negative carrier frequency. Nobody ever cares about it because you don't know what to do with negative frequencies, but mathematically, there's a negative carrier. And then when you actually have modulation for AM, you've got, this kind of wave shape. You got the carrier and you got the sidebands on either side of it up here, but you also got this imaginary negative image down there too in the mathematics world. It starts to pop up when you're doing digital signal processing because that's all mathematics. So you have to take account for those things. This is just showing what the fundamental is, and then these spurs and harmonics versus other noise that you're going to see. So this was a second harmonic. You'd have a third out here somewhere, not showing it. So what's meant by the term baseband in radio communications?
Charlie,
Well, let's
From-
see. I think I've heard different answers.
It's B, the message. Magic word message.
Prior to modulation, it's the input signal. Because after you modulate it, you get the sum and difference. It's no longer baseband, it's modulated. So what are the principal frequencies that appear at the output of a mixer circuit?
Charlie,
Charlie,
Charlotte.
carrier plus the two sidebands.
What occurs when the input signal levels to a mixer are too high?
alpha,
Alpha, always.
Yeah, alpha. Because you're going to get harmonics, and they call those spurious mixer products because you don't want them. Okay. Single sideband, the special case of AM, where we use a balanced modulator as opposed to a simple modulator circuit. And the difference is a balanced modulator cancels out the carrier. So all you get out is the two sidebands. basically the sum and difference without the carrier. And then you have to get rid of one of them, either by filtering or doing I and Q and eliminating them by subtraction or addition, should be.
I got a question. An older Kenwood transceiver I've recently acquired in trade had an unbalanced, it was out of tune, balanced modulator for its 2 meter sideband, and it was distorted and so forth. Is a balanced modulator likely to age and get out of tune?
I don't know why. I mean, it's normally composed of like 4 diodes and 2 transformers.
Right.
I don't know what would change. I guess you could have a diode going bad.
Maybe it's the filter afterwards or something, but the sideband was distorted in that old radio.
Yeah, well, if the balanced modulator isn't balanced, yeah.
Okay, I'm just curious because I did a lot with them back in the 1960s, but haven't touched them since.
Okay. Well, this is kind of a typical circuit for a balanced modulator. A double balanced modulator uses 4 diodes, a little more complicated circuit, but it works a little bit better. But in either case, you're eliminating the carrier. So you get double sideband with suppressed carrier. So essentially the only thing you get out of it are the 2 sideband frequencies that are shifted up on either side of where the carrier would be, but you don't have a carrier, which is why it's much harder to tune in a single sideband signal because there's no carrier to lock onto. You got to figure out where it should be. That's why you get the rain barrel and the Donald Duck, and because you're not where the carrier is supposed to be. And there's no way to find out except by listening.
I would expect,
Yeah.
excuse me a second, I would expect the RC component aging to upset things in the case that I experienced.
Yeah. And I don't know about this circuit. You don't usually see those in the double balance modulator, but I don't know.
Well, I had to make adjustments on my old Central Electronics 20A. Had to make adjustments to get it balanced, and I can't remember exactly what that entailed, but there are some alignment adjustments in that Kenwood that I'm speaking of. Anyway, pardon the interruption.
Okay. So what's one way a single sideband phone signal can be generated?
I think
It's like A.
Think it's alpha? Yeah. I don't know. I wonder if I need a new battery. I get a lot of double bounces.
It's slow. There's
Yeah. I've been practicing my CW.
a problem.
Okay. So if I got an AM signal, I can demodulate it with a simple diode detector. Just a diode and a filter for filtering the high frequency out. And I'm recovering the envelope of that modulated waveform. I'm throwing away the carrier. One side of that envelope, yes. Well, if I did 2 diodes and stuff, I could recover both sides, right?
But that doubles frequency. So now what you're listening to is.
Oh, no. On AM, it's not shifted in phase. You get twice the amplitude down to 0.
Oh.
So the simple diode is just, you're right, it's just looking at the top or the bottom. This is what is this? an active one, where you're using a transistor to do that process. It's fairly typical what you see in little radios and QRP and stuff for demodulating. So how does a diode envelope detector function? Has to be alpha. Okay, so now if I've got a single sideband, I can't use the envelope detector because I don't have a modulated carrier. I just have baseband frequencies shifted in frequency. So I have to use what's called a product detector. And it's actually another mixer where we inject, sometimes they call it a beat frequency oscillator, because what it's trying to do is recreate the carrier frequency, or usually the IF frequency at that point, to get you back to kind of where you started.
Essentially converts sideband to AM.
Kind of, Yeah.
And then it uses an AM.
right.
That's what they call it.
But you've eliminated one of the sidebands, so you're only dealing with one.
Right.
Another typical circuit for, simple little radio that's doing single sideband with an FET. What type of detector circuit is used for demodulating single sideband signals? Remember, discriminator is used for FM. A phase detector is used in the phase lock loop. We'll talk about.
Charlie.
I'm not sure where you use a phase comparator. I'm sure there are some. FM receivers use a circuit called a discriminator or ratio detector to detect an FM signal. And it's really two different circuits. But the discriminator basically converts the frequency changes into amplitude. So you're converting from FM to AM of the baseband signal. This is a kind of a typical circuit I found. I don't understand how it works, but I have an idea, but still.
It's like hanging off your eye.
Yeah, it's coming in here on the primary. There's two lines.
Oh.
And it's somehow the change in frequency, as I understand, unbalances the circuit, and that's what you're looking at is the balance from the reference frequency. It's kind of, I don't understand how it works.
It's smoking.
Yeah.
What is the component on the right?
Excuse me,
Bob. What was that component on the right? What was that symbol?
On the right?
Back up to there, right, that.
I think it's a capacitor. Why one side is white, I don't know.
It's not their idea of an electrolytic, right? Like one side would be curved for that.
I wouldn't think so. It could be whoever drew it didn't fill that box in.
Yeah, the symbol for an electrolytic would have a curved element on one side, typically.
Yeah.
All right, thank you. Go ahead.
Yeah. And normally you don't see capacitors as those big, heavy blocks anyway, but I don't know.
That could not be a big capacitor, otherwise it close out the signal.
Yeah. So what is a frequency discriminator? This is a hard one.
David, delta.
Okay, single sideband transmitters
The discriminator was used.
for FM. That was the
What's used for sideband.
product detector
Long that.
as opposed to an envelope detector.
Yeah.
Right. In generating single sideband, they'll use, particularly if it's an analog radio, they'll use a balanced modulator or a double balanced modulator. You buy those from mini circuits in little packages. You don't have to make them. And you combine the signals and get out the sidebands. And then get rid of one of them so that you can transmit it. And then usually they'll have another mixer there to shift the frequency up from the initial. Because all you're doing initially is mixing the carrier and your audio or baseband to generate your two sidebands, and then you eliminate a sideband, and you'll have a circuit there to select which one you want, because you have to use different filters. And then you mix it again with the local oscillator to get it up to the transmit frequency that you want, whatever band you're transmitting it on. So for a multi-band transmitter, the only thing that would change is this output part over here of what frequency band you're going to shift it to, because the other part is going to be the same. You're really generating it at an IF frequency, and then you're going to do a frequency shift. And let's see, the filter, which filter? Oh, the sideband filter. Yeah.
That's where they take sideband that, or take the carrier.
Right. Well, no, the carrier's gone at the balanced modulator.
Yeah. It seems to be.
The sideband filter filters out a sideband.
I thought there was, you shift the IF a little bit before the sideband filter, that's how you pick with upper or lower. I don't know.
Maybe,
Yeah,
maybe.
lacking that.
Yeah. Well, it's a simplified block diagram.
Yeah.
And this is a double balanced modulator. Notice, in some ways it's simpler. It's got 4 diodes, and I can't tell you how that works either. I tried to go through it once, and it's kind of, it looks too digital to be working in the analog world, but it's because you've got positive bias on the diode, so it's conducting AC. Anyway, what you get out is these two sidebands, and this suppress, or this carrier should be, you essentially get nothing or almost nothing. You might still have, sometimes they call it vestigial, and so vestigial carrier, and sometimes they leave that in. I think in the TV world, if I recall.
Old TV.
The old TV world. Yeah. Oh, homeowner. Who's homeowner? Okay, so what output is produced by a balanced modulator?
Double sideband.
Delta, David.
Yeah.
Dunkin' Donuts. That would be,
Yeah.
Double sideband suppressed carrier. What circuit is used to select one of the sidebands from a balanced modulator?
Bravo.
Bravo, Baker, Bravo.
Bravo, yeah.
Usually a pretty good filter,
Well, crystal glass filter.
crystal filter.
Little box.
How is a product detector used?
Delta,
Delta. Let's see. When we talk about receivers, one of the most important things is sensitivity. So it measures the minimum discernible signal level, or sometimes referred to as MDS. Really
Excuse
good
me a sec.
receivers.
Excuse me a second, back on filters. I believe that the ceramic filter technology has matched or exceeded the crystal filter technology. Anybody confirm or deny that?
No, but I would believe it.
Okay, good enough. Go ahead.
Most of the top of the line receivers have a sensitivity of less than a microvolt, whether or not they got a preamp in or not. So,
So,
yeah, which is what this is supposed to be,
okay.
quarter of a microvolt. Doesn't do you any good on 40 meters, though.
How far above the noise floor would signal have to be then? Yeah.
I don't know.
Because the receiver sensitivity, that always, they don't use a noise floor, they just have a source signal to keep turning down. And
Yeah.
stop detecting if that's the sensitivity.
Right. Kind of like the hearing test, where they keep getting lower and lower.
Yeah.
I think that's how they measure it. Gain is another one, okay, that affects it. The noise figure, obviously, and what the bandwidth is in your pass band or demodulator stage. But like I said, if you're looking at low band HF, there's so much atmospheric noise that that's not a very important factor.
Sensitivity is not your friend then.
Right. And gain isn't necessarily either. Sometimes an attenuator works better than. So what parameter affects receiver sensitivity? Everything.
oh,
Okay. Probably the most common of the analog, well, and even SDR radios are kind of superheads, was the super heterodyne, which came after the heterodyne, because in the heterodyne, it was kind of a single conversion. The super heterodyne was multiple conversions, 2 or 3. You could have 2 or 3 different IF stages. In most of the old AM type radios, you'd finally wind up with probably a 455 kilohertz IF. If it was an amateur type, it might even be much lower than that frequency for maybe a third one. Let's see. So in this case, you're using the mixer to essentially mix your RF signal with the local oscillator, which is essentially tuned to your frequency you're trying to receive, plus or minus the intermediate frequency. And then out of that, you get an intermediate frequency, which is that difference with the sidebands. And you filter that and demodulate it. In this case, they call it a super het. To me, it's only a heterodyne. because it only has a single conversion. But I'm not going to argue with them. And then you demodulate it with your envelope detector and amplify it and listen to the music.
7,200.
If it's a single sideband receiver, I'm still going to possibly have an RF amplifier. Most radios have one a preamp you can switch in at maybe one or two gain levels, and also an attenuator. I bring the signal into a mixer with the local oscillator, and which is a balanced mixer. So then I filter out the sideband. I may go through another amplifier, and then I do my product detector with the BFO oscillator to get it back basically to supply a carrier again. And then audio amplifier, and I'm done. When you look at the single sideband where the carrier should be, and then you see either the upper sideband or the lower sideband, and you notice they're mirror images. The frequency is inverted. If I'm doing an FM receiver, pretty much the same. I do the mixer, the oscillator, the IF amplifier. Typically they'll be, because it's always been 10.7 megahertz IF. I guess they still are, although I don't know what they do in more digital TVs. Then I go through the limiter circuit, okay, which is like an ALC. Okay, it limits the amplitude of the signal at that point. So it's a constant amplitude fed into the discriminator. I can't tell you why, but discriminator circuits don't work well if you have varying frequency and varying amplitude. Because I think part of the way it works, it assumes you've got a constant amplitude as some sort of reference. And then you do your de-emphasis to compensate for the pre-emphasis that you did when you generated it.
Excuse me a second, Bob.
Okay.
Discriminators typically have a limited linear range, and that's the reason for the limiter. The discriminator has a limited operating range that's more or less linear, and so the limiter is needed to keep the discriminator in its proper range.
Okay, well, I thought it had to do with the amplitude changes. Maybe we're talking about the same thing differently.
Oh, typically a discriminator is for FM detection.
Right.
And the discriminator circuit has limited linearity. Therefore, the limiter is typically needed to keep the discriminator at the proper operating point.
Okay. So the bottom line is the discriminator is used to convert that IF signal to AF.
What's the emphasis on
The de-emphasis,
that emphasis?
pre-emphasis on the transmitter.
Oh, okay.
You transmit with pre-emphasis.
Okay, got it.
So you got to get rid of it over here. So you're compatible with phase modulation. I don't know why that is an issue, but it's what it says in the book.
Could an FM receiver receive and deal with phase modulated?
Yes.
So why have the two different?
What do you mean?
What would be the advantage of?
Well, they do that so that it does both. It can accept phase modulation as well as frequency modulation.
So our broadcast stations that are FM could be PM, and we wouldn't know the difference.
Right. I've been told that you can't hear the difference of whether it's being sent FM or PM.
So is there advantage of one over the other with FM and PM?
If you look at the equation, it's simpler to do PM.
Yeah, that's all.
There's some extra,
It's all PM, it's cheaper to make them.
yeah.
It's like with both things and.
I don't know what they
They
are.
could be any,
Right.
no, are the components smaller or cheaper or something for PM as well as the?
I don't know.
That'd be a good question for extra credit.
Yeah, yeah. See if you get extra credit.
Okay. I'm using a stereo, that's all.
Okay. So when we talk about SDR, usually transceivers, you don't see SDR transmitters and receivers separate anymore or ever. You still have separate transmitters and receivers in the analog world. In fact, a guy was talking to me yesterday. He's got an old Heathkit transmitter, the separate one that he's having an issue with. In the SDR world, and I've seen it done in the analog world also, but in the SDR world, you always use I and Q signals. I stands for in phase, Q stands for quadrature phase. In other words, 90 degrees out of phase. So your input signal or the in phase is typically the cosine. So the Q is typically the sine. And that's how you deal with it in the software world of an SDR. And that's all I and Q stand for is in phase and quadrature phase. Remember, quadrature is a quad or 90 degrees. So with those, you can do virtually any kind of modulation or demodulation if you know enough mathematics.
Totally down.
And this is kind of a typical circuit. They use a common local oscillator or synthesizer. In this one, it's showing in order to generate I and Q, you bring your signal in and then you mix it in two different mixers that are fed the carrier signal out of in phase and out of phase, and that gives you your I and Q outputs. And then you do some processing and filtering on those and run it through an analog to digital converter back into the analog domain. Oh, wait a minute. Oh, no.
They're all pointing in the wrong direction.
Yeah, because we're still analog here.
Yeah.
Yeah. This is a hybrid SDR. It's not direct conversion.
There it is.
Hey, Walter.
I popped my head in here, we were doing some work next to us.
Oh, okay.
Keep going, didn't want to disturb you, I read some pictures.
Were you responsible for our power glitch?
Yeah. For what, lit?
We lost power.
Yeah, I just pulled up here just a minute.
Oh, okay.
We were probably doing the car show.
It kind of messed things up.
No. Well, that female's problem, I guess.
A DDC and a DUC. This is all the stuff that's in that FPGA that's doing all the digital processing, the digital filtering and the Hilbert transform and all that good stuff that's going to go on. And eventually you get data out or you're putting data in and getting it back to the analog world. In a direct conversion, this I and Q typically is generated within the processing. So you're feeding the signal directly into an analog to digital converter and then operating on it in the digital world. In this case, they're doing that. And this radio is kind of a hybrid. It uses what's called a halo detector to generate the I and Q signals by sampling at 4 times the signal rate plus the offset of the IF. Which of these functions is performed by software in a software-defined radio?
All of it.
Yeah. Oh,
What's an advantage of using I and Q signals in a software-defined radio?
Problem.
It should say all types of modulation and demodulation. What's the phase difference between the I and Q signals that software-defined radio equipment uses for modulation and demodulation?
like,
Mhm.
like, all lines.
90 degrees or quadrature? Okay, so who's that? We did all that stuff, so. Am I still recording?
Walter must be helping us again.
Oh, there we go. It should, normally it shows up down there in the more.